This lecture is about separation of variable for heat equation. I have already covered in few lectures the following material: linear operator, adjoint and self-adjoint operator, superposition principle. When you have a linear differential equation has multiple elementary solutions, you make a general solution by using superposition principle. Orthogonality of functions. We are not expecting at this stage to understand Fourier series. Without knowing Fourier series, I'm going to cover separation of variables because the idea is to cover all level of students. For instance, students who are taking a PDE course from mathematics department, or maybe students are taking a comprehensive exam in mathematics, PhD comprehensive exam in mathematics. So they would eventually know and learn Fourier series, but maybe students from physics or engineering, they might not have learned Fourier series in details, but want to understand separation of variable for solving linear differential equations. So that is why I just want to go with basic knowledge of orthogonality. Eigenfunction of linear operator that is needed, separation of variable for first order ODE which is needed, and this is something we cover a lot. We talk a lot about it in first year courses. Separation of variable for PDE is the main content of today's lecture. So hopefully I will be able to illustrate with one simple example covering the key concept, and you can go ahead and try other example and see if you can understand how to solve linear partial differential equations in one space dimension for now. So let's start with an example. So simple one-dimensional heat equation, a heated rod of length 1, 0 to 1, which is the domain. I have a Neumann condition here. du dx is 0 at x equals 0 and x equals 1, both end of the heat. So this is insulation boundary condition or insulated boundary condition. In terms of heat equation, it is understood that at both ends the rod is insulated, so no loss of heat. Mathematically, this is called Neumann condition. And then we have the initial condition, which is 50 times x times 1 minus x. And once we find the solution, we also want to find what will be the temperature in a limiting case after a long time. So t is the time variable, and if t goes to infinity, what will be the temperature? Okay, so the solution procedure, we are going to use a elementary solution or trial solution. Lambda, I'm going to take a positive number, and maybe lambda also can be equal to 0, and this is just you have two parts of the solution. Maybe I can rewrite the solution u, which is a function of x and t, and then you plug back into the PDE. So differentiate with respect to time, lambda s, lambda t with negative sign on the right hand side. I'm going to use k for the diffusion coefficient for now, s double prime e to the power minus lambda t where k is 0.001. In order to avoid writing down 0.001, I can just write an arbitrary constant k, and then once I have the solution, I will substitute k equals 0.01. That's the idea. Okay, so you see that you can cancel e to the power lambda t from both sides. So e to the power minus lambda t is not 0. E to the power minus lambda t is not 0. They can cancel out. And then you are left with k times s double prime equals minus lambda times s. So we can rearrange that. S double prime equals minus lambda divided by ks. Okay, so we can have the boundary condition because the original PDE has Neumann boundary condition. So this one will have also Neumann boundary condition. So S prime vanishes in both ends. And from ODE knowledge, we already know that this is a second order boundary value problem. Its solution or eigenfunctions are either sines or cosines. So, and there are an infinite number of eigenfunctions. So we will put a subscript Sn, maybe as a function of x, and it will be sine n pi x, because the domain is 0 to 1. So sine n pi x, one sine wave for n equals 1, and multiple sine waves depending on what value of n. Okay, or cos n pi x. Okay, so we need to satisfy the boundary condition. Obviously, we see that S prime n x is, if I take sine, that will be cos. So that will not satisfy the boundary condition. Maybe we can just write the cos part here, minus n pi sine n pi x, and that indicates S prime n 0 is 0, S prime n at 1 is sine n pi times sine n pi. For n any integer, sine n pi is 0, which is also 0. But if you take sine n pi x for your solution, then the derivative of sine is cosine, which does not vanish at the boundary. So we are not going to take a sine solution. So this is something, by looking at the boundary condition, you decide which are the eigenfunctions for your heat equation. Okay, so that's all for now. Then you go to the next step. What is the next step? You want to find what is the eigenvalue. So you differentiate for a second time. So if you differentiate for a second time, you get n square pi square cos n pi x. And then you compare this with lambda minus lambda over k s n, which is a function of x. Okay. So then you see that by looking at this part, which is negative n square pi square, and this part is negative lambda by k. So that means you can just ignore minus sign. N square pi square is lambda over k. So n square pi square is lambda over k. Then you can see that k goes to the other side. So you can say, okay, lambda is k times n square pi square, and we know k is 0.001. We'll come back and substitute that once we are done. Okay, so now that's another point here, whether lambda can be 0 or not. So why we choose in the original substitution lambda is greater than or equals 0 is because we want that the solution must decay. So if lambda is negative, then e to the power minus lambda t will be positive and solution will blow up. Lambda can also be 0 is because of the Neumann boundary condition. There could be nothing to lose or nothing to gain, and lambda equals 0 corresponds to just ux is sx. So let's call that s0x. So s0x, and s0x, if I think that okay, s and x is cos n pi x, s and x is cos n pi x, and s0x is just 1. Okay, so then you have 1 is a solution, or you could also take a constant as a solution, but obviously 1 is a nice solution instead of an arbitrary constant. Eventually we will have an arbitrary constant by principle of superposition. Okay, so then what is the summary here? By doing all those things, we can see that 1 is a solution, and cos n pi x for n equals 1, 2 up to infinity are solutions. I have just intentionally taken one separate. You could say, okay, cos n pi x is a solution for n from 0 up to infinity. That also works, it's the same thing. So now use the principle of superposition. So the principle of superposition states that the linear combination of all elementary solution or trial solutions are the general solution. Makes it a linear combination makes the general solution. Okay, so then a linear combination, you take all of them. So maybe you take a0 times 1 plus a1 times cos 1 and 1 pi x. That perhaps we have already practiced from other lectures, or even for this lecture individually, we can say, okay, I can take a sum over n from 1 to up to infinity cos n pi x and e to the power lambda t. We started with minus lambda t, so minus k n square pi square t. Okay, so maybe some clarification would help some of you. So let's see here. So the solution we started with u x t equals s of x e to the power minus lambda t. Okay, so one solution would be s0x e to the power minus so n is 0, so e to the power 0 t, so which is just 1. The other solutions are snx e to the power minus k n square pi square t. Okay, and snx is cos n pi x. So some of you might be wondering why I have a e to the power minus k n square pi square times t inside the sum when I take the superposition principle, and why not here? So that is something perhaps you think of first at this stage coming here. Okay, so I have 1 is a eigenfunction, cos n pi x is another eigenfunction. So 1 is s0, cos n pi x is sn for n not n greater than 0. Okay, So then you think of elementary solutions here, and then you take all the elementary solutions and then make a superposition principle, apply the superposition principle by considering linear combination. Then you can clearly see how the constant term comes. Okay, so now we want to determine the coefficients A0, A1, A2 or A0, AN. Okay, so this is something we will be using the orthogonality. 1 cos n pi x. This forms a set which is orthogonal. Okay, so we will multiply by one of the function from this orthogonal set, multiply this series, one of the functions. So let's say multiply by S0x, which is 1, and integrate. So that is where we are using the orthogonality. So 0 to 1, well, maybe that before talking about the multiplication, one more step we should perhaps look at here. Okay. So let's put here t equals 0, the initial condition. So u x0 equals a0 plus n from 1 to infinity an cos n pi x. Okay. And then you multiply by S0, or which is 1, and integrate. So if you do that, then on the left hand side, let's first write down for clarity dx equals a0 is just a constant, 0 to 1 dx plus, well, because of the orthogonality, if you just think of the orthogonality, then this term is not 1. Or let's say here, this term is not 1, is cos nx, and 1 and cos nx. Orthogonal means if you multiply by 1 and integrate it, that will be 0. You can easily see here that if I multiply by 1 and integrate, so integral of cos n pi x in 0 to 1 will be sin n pi x at 0 and 1, okay, and which is 0. This is very clear that if we integrate cos n pi x in a certain domain from 0 to 1, which is the half wavelength, then the integral is 0. And on the left hand side now, you go ahead to substitute 50x times 1 minus x dx, and then on the right hand side you get simply a0. Okay, integrate on the left hand side, take 50 out, x minus x square, that would be half x minus 1/3 x cube, and evaluate at 0 and 1 a0. Then you get 50 times 1/2 minus 1/3. When x equals 0, it is 0, so minus 0 a0, or a0 6, 3 minus 2 is 1 by 6. So 50 divided by 6, you can write 25 divided by 3, so which is a0. And very similarly, you can find the other coefficients. So for the other coefficients, you can think of multiplying now by cos pi x, n equals 1, and integrate. Then you multiply by cos 2 pi x, integrate. Then multiply by cos 3 pi x and integrate. Every time you do that, so this one maybe at this stage I can rewrite. For some of you it will be more clear. This is a1 cos pi x plus a2 cos 2 pi x plus blah blah blah. We continue there, right? Okay. So if you think of this way, when you multiply by cos pi, so this term is cos pi x, and integrate, this term will be non-zero, this term will be 0, this term will be 0 because of the orthogonality. When you multiply by 2 pi x, this term will be non-zero, all other terms will be 0. And if we realize that, and if we already have seen that in other lectures in the classroom, we can think of just multiplying by cos nx in general. So u x 0 cos n pi x dx on the left hand side, and on the right hand side obviously we'll be looking for n from 1. So first term will be 0, and then from second term onward, each term, one term will survive for each value of n. So we can write that from 0 to 1 cos n pi x, which we have. We multiply cos n pi x dx. Okay, so now little bit of work here to finish the integral. We have to be slightly careful not to make mistake, and we do one at a time. Let's look at left hand side. Substitute ux0, which is 50x times 1 minus x, multiply by cos n pi x dx. Okay, and n going from 1, 2, 3 up to infinity. On the right hand side, well, this is a very easy integral. Something we can use trig identity. So you see that cos n pi x times cos n pi x. So you can just ignore n pi. You can think of, okay, just cos x times cos x, or cos square x. If you multiply by half, then you get 2 cos square x. And 2 cos square x is 1 plus cos 2x. Then the integral will be 1 plus cos 2x. 1 plus cos 2x. So you multiply by half, and then you will get 1 plus cos 2x, which has to be integrated from 0 to 1. So if you integrate 1 from 0 to 1, you get 1. So don't worry about half, just half. Cos n pi x, if integrate from 0 to 1, is always 0. So this is one way of looking at it. And since we are practicing a lot these days with separation of variables, so if you have done other problems solved, and then you have already seen that this integral is L divided by 2, or when you looked at the orthogonality, we have said that L divided by 2. So I just don't want you to memorize this as a formula, L divided by 2. Rather, it's very easy to think and solve it using mental math. That once you have cos multiplied with cos, you are integrating from 0 to 1. I think a little bit the way I just said how it is half, and then you will be very comfortable. You can do math without memorization. That's the objective, because we don't want to memorize math. Okay, we want to understand, and also we want to minimize the calculation. So on the left hand side, it is integration by parts. So integration by parts formula, maybe that we need a rule how to do integration by parts. So I will write u dv. I know the formula is written in different part of the world in different way, but this is very standard one is u dv. These days almost all textbooks are talking about using u dv. Okay, so u dv, it goes to uv, and then leave even another integral 0 to 1. So we don't have the limit in this case, b du. So we identify this part in this case, db, and then u is 50 times x times 1 minus x. So then we get 50x 1 minus x. So what is db? So db is, you can just think a little bit. So you integrate that. So 1 over n pi sine n pi x dx integral, you get 1 by n pi sine n pi x when you integrate cos, right? So dv is cos n pi x dx. Cos n pi x dx is dv. So you just think of here, differentiate that sine n pi x, the derivative will be n pi. So n pi cancels, cos n pi x. So I get it, cos n pi x. Okay. And then I have another integral. This will be evaluated from 0 to 1. This will be evaluated from 0 to 1. And then I will have a second integral from 0 to 1, and this time v du. So u part has to be differentiated. So let me just do it here. So I multiply by x minus x square, so it will be 1 minus 2x and 1 by n pi sine n pi x. So that is v du. So I have a dx, and on the right hand side half an. Okay, so looks little bit of pain, but should not be very tedious. You can just look at some trick in mental math and you'll be fine. So you see that here this one is sine n pi x evaluated at 0 and 1. So this one is 0, because sine 0 is 0, sine n pi is 0. Then we get another integral here. One more steps of integration by parts, and now I have a minus sign. I have to be a bit careful. So I put a minus sign here, and I identify that 50 and n by pi constants that goes out of the integral. Again, so u db. So u is 1 minus 2x. U is 1 minus 2x. So maybe I put a bracket to ignore the coefficient, 50 by n pi. Maybe that would be a good idea. And then I have sine n pi x. So antiderivative of sine n pi x will be minus 1 by n pi cos n pi x. And that will be evaluated at 0 and 1. Okay, minus now integral from 0 to 1, and then we have to write down v du. V du. So we know v is, we have already found cos n pi x with a cos n pi x with a coefficient of minus 1 by n pi, and u is 1 minus 2x, so du would be very much minus 2 dx. Okay, and on the right hand side is half a n. Okay, so this time you have to be a bit careful because sine n pi is 0 for any value of n, cos n pi, so cos even pi is 0 but cos odd pi is negative. Cos even pi is 0, cos odd pi is negative. That's our reminder here. So we have to consider this part for n even or n odd. So for n even, so 1, and for n odd is other. So let's first try n odd. So if n odd, I will write minus 50. Maybe I can just take minus, see here, minus 1 over n pi out. So it will be plus n square pi square. And then evaluate at x equals 1, which is 1 minus 2 is minus 1. And cos n pi x. Cos n pi x. N is odd. So this is also minus 1. N pi 1. Right? If you substitute x equals 1, n pi 1. Okay. Minus. So this time x equals 0. So 1 minus 2x is 1. And cos 0 is just 1. Okay. And minus, that will perhaps be minus minus plus, minus minus plus 2. So, and then you can see the integral of cos n pi x. Integral of cos n pi x, antiderivative of cos is sine, and evaluate at 0 to 1. So that will be 0. So that's what we know. We integrate cos from 0 to 1, we get 0. So that is 0. Okay. So this gives me a n equals 0. So it's not for all a n. A1 is 0, odd number. A3 is 0. A5, A7, A9, and so on. They are 0. Okay. So now we evaluate n even number. So n is this time even number. If n is even number, what we do? We just follow the previous step, but now we will have here minus 50 divided by n square pi square, minus 50 divided by n square pi square, and then I have 1 minus 2x, which is minus 1, but now n even, so I will have plus 1 minus 1. Okay, and next part is the same, and even or odd, you integrate cos, you'll end up with 0. So this equals half a n. So what we see here, you just do a little mental math. So minus 1 minus 1 minus 2. So negative 2. So negative negative positive 100. You take this a here. Okay, so there is a typo here, so that should be plus. We already have found this one is plus because of this. Okay, so then you have negative negative negative, so a n is negative 200 divided by n square pi square n is even. Okay, so now we can write down the solution. We can write down the solution u x t. Now the solution, which is the first term, is 25 divided by 3 plus we could manipulate the series, but just we like to be very simple. You know that n equals 1 is odd number, so we'll start from n equals 2, and then we will say okay, n even, and go up to infinity. So we will start with 2 and go to 4 and so on, and an is minus 200, negative 200 divided by n square pi square times cos n pi x e to the power minus n square pi square k. And this time I will just substitute the value of k, t. That's all. This is the final answer. So the solution of heat equation for Neumann boundary condition for the given initial condition is this. So this means if we have to solve another problem of heat equation on a different domain, one special dimension, on an interval, on a different interval, different boundary condition, with a different boundary condition, of course the eigenfunctions may not be cos, will be sine, or maybe a mixture of sine and cosine. You find out by following the steps without memorizing anything, but then we will end up with a solution of this form, and it is an infinite series. It is a series solution, but you can see that each time n increases, this term becomes small, and very small multiplied by this term. Again here is divided by n, so n increases, this term also becomes small. So very quickly those terms goes to 0, and if we just think that n is very large, then maybe we can just approximate the solution, assuming for large, it is not a limit, or when n is large, I would say if n is large, or if t is large. Let's say if t is large, what happens at t is 200? Whatever the value of n, those terms will be very small, so we can neglect them. So we can say okay, for large n or large t, the solution u of xt is approximately 25 over 3. Please note, I am not trying to provide you a good introduction or analysis about asymptotic analysis, asymptotic form of the series. It's just giving you a hint. So just be careful this part. If you get confused about how we get it, this is just not the limit of the sum. This is just, I'm considering that what happens of the temperature on the rod when T is large. So when T is large, you have already all those terms very small, and approximately you can find it 25 divided by 3. Thank you very much. If you have any question, feel free to contact me.